Hello, Space Science. Welcome to your second lesson on spectroscopy. Last time you learned about how to look at and analyze emission spectra, and from there learn about the chemical composition of a star. Today we're going to learn about the relationship between the spectrum of a star and its temperature. Now before we go there, we need to revisit the electromagnetic spectrum. So again, you know that there are different types of waves, different types of electromagnetic waves, and they differ because of their wavelength. Now, just a reminder, these waves to the right of the spectrum, gamma rays, have a high frequency and a low wavelength. What this means is that they are high energy. So the high frequency, that means they're going up and down very rapidly, means that they have high energy. Now by comparison, some of the longer wavelengths have a much lower energy. Now when we talked about emission spectra, we were really just talking about visible light, about capturing and deciphering, separating out with a prism the visible light emitted from a star. But stars emit all types of light: radio, microwave, infrared, visible, UV, X-ray, gamma. And we can create spectra that span the whole range of the electromagnetic spectrum. And you might not be surprised that there's a relationship between the type of electromagnetic wave a star lets out and its temperature. Now, if these shorter wavelengths are very high energy, you might be able to predict, and you would be correct, that these waves are going to be let out by hot stars. Now, of course, all stars are burning hot, so it's just a question of relativity. So the relatively hot stars are going to be letting off much shorter wavelengths, because those shorter wavelengths are actually very high in energy. Now, by comparison, cooler stars, now, either way, we're talking about several thousand degrees, so it's all relative. Cooler stars are going to let off much longer wavelengths. And so we can predict the relative temperature of a star based on something called its thermal spectrum. And you have an example down here. So you've seen examples of stellar spectra, and you know that they're full of zigzags, as is the case right here. This is what a star's spectra might look like. And these zigzag lines, the deep ones, are absorption lines. Those are lines where certain chemical elements are absorbing very specific wavelengths of light, and so that's code for us that those chemical elements are present in this star. But you'll notice that even if you ignore these big dips, the spectrum itself has a bit of a shape. Right? It's got a sort of hump at the beginning, and then it falls a little bit. That doesn't mean that this area over here is all kinds of absorption lines piled on top of each other. It means that this star just happens to let off relatively more short wavelengths than long wavelengths. So if you have to look at the numbers on the wavelength scale, these are the shorter wavelengths, these are the longer wavelengths. So this star is letting off shorter wavelengths, and this symbol I just drew is the symbol we use for wavelengths. So what that means is that this star is on the hotter side, right? Because it has this bump, it has this sort of hill that's showing it's letting off a much higher frequency of short wavelengths. And I showed you up here that short wavelengths, right, low wavelengths mean high energy. So let's look at another set of examples. So if I look at these two stars here, again I see all of these dips, right? And the dips are absorption lines. The dips represent the presence of certain chemical elements. When I'm looking for information about temperature, I'm looking at the overall shape of the spectrum. So if I compare these two spectra, this has its peak, its thermal wavelength peak, at about, let's call it 4,800 angstroms. Angstroms is a unit for wavelength. Over here, the peak of the wavelength is much closer to about 8,500 angstroms. So if you were to ask yourself which is the hotter star, you have to ask yourself which one is letting off shorter wavelengths. Now, 4,800 is a much smaller number than 8,500, so the very first star is going to be much hotter than the second.